Because
I have a question.
Sure.
So will it roughly be like 24 questions? I'm not sure if you've already said this or not in your emails, but like for Wednesday?
Yeah. So just like the other tests, the practice test should give you a pretty solid idea of what to expect. But like I said, so I did say in my email, the order of the questions will be different. The types of questions in there will be, I say the same. I know as a student that's like, hey, these weren't the same. But in my mind, you know, the same types of questions I'll be asking. So.
Okay, thank you.
No problem. All right. Let's do them kind of in numerical order. So we'll do question 4B for those who don't like fractions, and then we'll move to 18, 19, 20, and then I'll just keep an eye on the chat if you kind of come across something. Let me grab it. Oh yeah, who likes fractions, right? Here we go. So I'll just say practice final select solutions, right? I figured for the final exam, it should be a little bit hard, so I'm not posting full solutions to everything because then I worry that someone could come after me and say, hey, they basically had the whole solution. You can just do the final from there. So that's why I'm making it a little bit harder, but not really. All right, so it sounds like A is fine. So let's do B. All right, so the pickle is we've got the 7/2 and 3/2. We notice that x minus 3 and x minus 3 is something that we can pull out a common factor, but we have to remember how these exponents behave, right? So exponent loss. Now, if I have the same base, right, then I add the I add the exponents, right? I'm thinking x squared plus x to the 3 is x to the 5, right? So I have to add exponents. So if I want to split these up, for example, if I want to bring out this 3/2 and kind of pull that off to the side, I can rewrite 7/2 as 3/2 plus 4/2 because they have that common denominator. So this is what this would look like, right? We've got x minus 3. You know what? I'll write out the full question just to be proper here, and then I'll kind of make a note of what I'm doing. Factor out a common x minus 3 to the 3/2. Okay, so what this becomes is I get x minus 3 to the 7/2 becomes, let's say, 3/2 plus 4/2, right? Here I've got a common denominator, so I don't need to deal with those fractions, but I've got 3/2 plus 4/2, right? 3 plus 4 is 7. So I'm allowed to split them up like this. And then the next term is just going to be the same. So minus 9 times x minus 3. I'm just writing it out so I have it all the way through. All right, so now I can rewrite this as two terms, right? X minus 3 to the 3/2 times x minus 3 to the 4/2. 4/2 we can simplify. I'm going to keep it as 4/2 for a little bit longer just to highlight that that's where it came from, right? But 4/2 is just 2. So here we go. We get x minus 3 to the 3/2 times x minus 3 to the 4/2. Right, in the next step, I'll rewrite it as just x minus 3 squared. But like I said, I just want to emphasize where that 4/2 is coming from. And then this next part just stays the same, minus 9 times x minus 3 to the 3/2. Okay. So now I can pull out a common x minus 3 to the 3/2 outside, right? Because I've pulled it out from both of these terms. So this becomes x minus 3, oops, if I can, x minus 3 to the 3 over 2, and then I'll put in big brackets, x minus 3, and then now I'll write squared. 4 over 2 is just the power of 2, and then minus 9, right? Because I've already pulled out this x minus 3 to the 3 over 2, right? So, but don't forget that minus 9. That's a pretty common mistake that people make, okay? So now we're feeling good about ourselves, and then we go to check our answers, and we're still not quite there. Nope, because we can expand this a little bit further, right? And so let's see, factor the expression completely. So I would, so here's the thing. It's hard as a student, it's hard to know, especially when you're beginning, it's hard to know that you should keep going here and see if you can factor some things out. But I would probably just try expand this out. If it gets really big and nasty, then go back and just leave it as it is here. But usually if you just expand this out, some things will cancel, right? And that's what we are hoping for. So let's see here. So now on the outside here, this x minus 3 to the 3 over 2, I've already factored that out. So I'm just going to leave it hanging. It's not going to change. Now I'm working inside these brackets. So I have x minus 3 times x minus 3 and then minus 9. I always go really slow when I'm foiling these out, right? You're expanding x minus 3 squared. Is x minus 3 times x minus 3. So I always, x squared minus 3x plus 9. Hey, look, plus 9 and then minus 9. So, okay, so it feels like we're on the right track. All right, so let's do it. X minus 3 to the 3 over 2. Well, now I might show off, right? X squared minus 6x plus 9. But typically I would just take the time and show all that work, but we're on a time crunch. X squared minus 6x, right? Minus 3x makes minus 6x plus 9 and then minus 9. Wow, plus 9 minus 9 goes away. Looks like I'm able to extract a common x here. So I'm going to do that. I'm going to pull that common x outside here and then see what I'm left with. So x minus 3 to the 3 over 2, oops. And then x times x minus 6. And I think that's pretty, I can't see any other option for factoring any further. So we're done. Any questions about that one before we move to 18? 18, 19, 20 sound like trig to me. Awesome. All right. Then let's go see question 5. Oh, not now. Oh yeah, you got it. While I'm here. Hey, I didn't scroll too far. Okay. So question 5. You know what? I'll put it on its own page. Why not? All right. So we need to remember what the net change is and what the average rate of change is. The net change is f of b minus f of a, b being the rightmost point. So here, if we're talking about x equals 5 and x equals 5 plus h, we're really talking about a is 5, so our starting point is 5, and then we've moved h units right to the right. So here, I'm just going to make a note that you want to think of a as 5 and b is 5 plus h. Okay. So A is always your starting point, and then B is always your end point. In this case, you're moving from 5 to 5 plus H. So then in A, well, the net change is f of B minus f of A. Okay. So what you do is you have your function 1 minus 3x squared. And so f of B is 1 minus 3 times 5 plus h squared, right? And then minus f of A is 1 minus 3a, which is 5 squared. So what I'm going to do is, maybe I'll add an extra step. So you don't need to have this step, but maybe I'll write out f of A and f of B so that you can see where things are going in. Let's do that. So f of B is 1 minus 3b squared minus f of A. And notice I'm putting big square brackets around these things to keep them separate, right? You want to keep them as big lumps. So, and then, oh, so that's the next one. So that's the average rate of change. This one here. Yeah. Jump the gun. So I get you to do the net change, and then you use that to find the average rate of change. Awesome. Okay, so f of A then is going to be 1 minus 3a squared. 1 minus 3a squared. Okay. And so now I'm going to plug in my B and my A, which are 5 plus h and 5 respectively. So especially for the 5 plus h, you want to keep brackets around that whole 5 plus h. So this becomes 1 minus 3 times 5 plus h squared minus 1 minus 3 times 5 squared. Okie dokie. So we get big square brackets again here. 1 minus 3 times 5 plus h times 5 plus h. So what I'm going to do is I'm going to scoot this over because there's no way I'm going to have enough room, right? So we usually expand this out. In fact, you'll always expand this out. And the whole goal is to kind of simplify the net change as much as you can. And then when you use it in the average rate of change, it'll be a lot easier. So minus 1 minus 3 times 25, right? 5 squared is 25. All right. I get 1 minus 3 times 25 plus 5h is 10h plus h squared minus, and now I've got 1 minus 3 times 25. So 1 minus 75 is negative 74. Okay. So I get, now, because I'm so close to simplifying this here, these big brackets don't actually do anything. So I'm going to drop them out. You didn't need to have them there, just for me to be able to see which things hang out together. So 1 minus 3 times 25, and I am going to keep that minus outside so it doesn't mess with anything quite yet. So I get 3 times 25 is 75.
What happens if you were to do 1 minus 3 and then you did negative 2 and foiled it in?
We can't do that because BEDMAS, right? Brackets, exponents, division and multiplication happen first, and then we add or subtract.
Okay.
Yeah, so it wouldn't work out if you did the 1 minus 3 first. So you want to be really careful that you keep the multiplication and do the subtraction last.
Okay.
Good. So plus 30h plus 3h squared, and then plus 74 negative, subtracting a negative makes adding. Now I'm going to bring this negative inside so that I can slowly dissolve all these brackets here. So I get 1 minus 75 minus 30h minus 3h squared plus 74. So it looks to me like here, 1 minus 75 is negative 74 plus 74. So those will dissolve away. So I'm not even going to bother with those. I'll just cross them off right away. And then depending on, I can't remember how I wrote it in the solutions, but it doesn't actually matter. Just leaving it like this is fine, right? So the net change then is negative 30h minus 3h squared. Okay. You can pull out a common negative. You can even pull out a common 3. I wouldn't bother. I would just leave it like this. Now, in part B, we want to find the average rate of change. The average rate of change is the net change over B minus A. Okay. So the average rate of change is the net change over B minus A, which is the same as f of B minus f of A over B minus A. So that's the one Tyler jumped to, which is good. It's always where we're ultimately building to. So if you just went right to it, that's fine. Okay, so we already know that f of B minus f of A is negative 30h minus 3h squared. So I'm just going to take that and bring it in. So here, this becomes negative 30h minus 3h squared over B, which is 5 plus h, minus A, which is 5. So notice what happens here is that and this is always going to be the case, 5 plus h minus 5, you're just left with h. And then that h is going to cancel with one of the h's factored out in the numerator. So this becomes negative 30h minus 3h squared over h. Now, I'm going to show the h factored out in the numerator just to emphasize that it has to, so in order to cancel this h in the denominator, right, I have to have an h multiplying everything up top, right? Otherwise I can't do it. So, so I'm going to emphasize that by pulling one out and then canceling. If you just went straight to canceling here, that's totally fine. Okay. So I have h times negative 30 minus 3h over h. This h is going to cancel with this h. And so the average rate of change is negative 30 minus 3h. Okay. All right. I'm going to jump to question 18. I'll keep an eye on the chat in case something comes up there. But let's do 18. Number 6, you got it. Just because I don't want to miss out on 18, 19, 20. How about we do 18, 19, 20, and then I'll go back to 6. Does that sound good? Deal. Perfect. Perfect, perfect. Because we didn't actually get to spend that much time on trig, so trig is kind of the reason I wanted to do this review session because we didn't really get a chance to review a lot of it. So one thing I will point out is you'll find the formula sheet that I posted on, I can't remember if I called it a formula sheet. Yeah, so on Moodle, I posted 2 formula sheets. One's called the Math 120, which is just the pre-calculus general formula sheet. The one that's really, really useful is the trigonometry formula sheet, okay? And it looks like this. So I'm actually gonna bring this into my notes here so that we can refer to it. Okay. All right. So how I want you to approach kind of any inverse trig function is, let's just do a little recap on inverse trig. So if we have the cosine of, we started calling the angle theta, you can call it t or you can call it x, it doesn't matter. But the cosine of something, and it's an angle, is gonna be, how did I want to approach this? I'm only talking about this guy here. Let me start over here. I'm going to say theta is going to be the inverse, oops, same color, inverse cos of 3/5. Okay. So here, so my first step is going to be to let theta be the inverse cos of 3/5. And that doesn't feel like it got us very far, but what happens is this inverse cosine can get shifted over to the left-hand side, and in doing that, we drop that -1, right? So it's no longer the inverse. So we can move this guy over here, and maybe I'll use pink, right? If I move it over here, it just becomes the cosine of theta. Okay. So now what we have is we have the cosine of theta is 3/5. If you remember SOHCAHTOA, or if you prefer to go to that formula sheet, right, specifically over here, right, this is SOHCAHTOA and a little bit more. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tan is opposite over adjacent. And then we've also got the cosecant, secant, and cotangents in the similar way. And of course, I've forgotten what we were, cosine, okay? So cosine, of course, is adjacent over hypotenuse. So what we know now is that the adjacent is 3 and the hypotenuse is 5. Okay. So here, cos theta is SOHCAHTOA adjacent over hypotenuse. Okay. It doesn't really matter what you make your triangle look like, as long as you have a right angle triangle, meaning you have a 90-degree angle in there. So what I'm going to do is I'm just going to draw some sort of right angle triangle. Okay. And I'm going to put theta down here. You could have just as well put it over here. It doesn't matter. Okay. We know that the adjacent to the theta here is 3 and the hypotenuse is 5. Remember, the hypotenuse is always the side that's opposite the 90-degree angle. So here we have the adjacent is 3 and the hypotenuse is 5. Okay. Now we're back to the Pythagorean theorem to try to figure out what this side is. And then what we can do is, then we kind of go backwards, and it feels weird, But then we remember, okay, well, we let theta be the inverse cos of 3/5, but then we also use the 3/5 to set up our triangle, right? But if we're just letting this whole chunk be theta, right, or the angle, then I can find the cosecant of this angle, right? Because the cosecant, and maybe I'll just do this, just copy this in here, so I don't have to flip back and forth the whole time. Right, then I can find the cosecant as the hypotenuse over the opposite, right? I already know the hypotenuse is 5, so I have to find the opposite. Okay. But I also know if I call this a, for example, right, then I know a squared plus b squared is c squared, right? C being the hypotenuse. So 3 squared is equal to 5 squared. So a squared plus 3 squared is 5 squared, right? That's the Pythagorean theorem, and I'm hoping that's kind of familiar. I'm pretty sure it might even be on this trig formula sheet. Maybe it's, we do assume that you know it. Yeah, which I think is fair. If not, right, this is the Pythagorean theorem. So you can look that up if it doesn't look familiar. Okay, a squared plus b squared equals c squared. So now if I have to solve for a, right, I've got 25 and I've got minus 9 here. I'm gonna have to use my 25 minus 9 is 16. Hey, looks good. So a squared plus 9 is 25. So a squared is 16. So a is plus minus the root of 16. But there's no mention of which quadrant we're in, right? And so then I can just assume that it's the positive. Okay. Assume positive. Okay. So then A must be 4. Okay. Later in the other questions, right, if we read this question, there's no mention of being in a specific quadrant. So that's why I'm saying we'll just assume it's positive. Later on, we'll be putting this triangle in a specific quadrant. So then X can be negative or Y can be negative. The hypotenuse is always going to be positive, I think, pretty sure. Yeah. All right. So then if I go back here, cosecant of cos inverse of 3/5, well, I replace this cos inverse of 3/5 with theta. So the cosecant of theta, therefore, the cosecant of theta from that handout is the hypotenuse over the opposite. Which is 5/4. So it's kind of like it's a daisy chain of events, right? And it just brings you back to some nice fraction, typically. Okay. So that was 18. Let me just check here. Next on the docket, 19, unless there are questions about 18. It is tricky, right? So, but just kind of follow this. So if you say, and you can even say, let theta be this, yeah? Then you can rewrite cosine of theta as 3/5, and then knowing how the cosine of theta behaves, you'll have to solve for the missing side using the Pythagorean theorem, and then you can rearrange the sides to whichever one of these that you need. I'll go grab 19. Oops, wrong page. Okay, so this is one of those where, and let me just, because there was something, is it this one or was it the next one? I had worked through some of them before. No, I think it was the next one. Okay. All right. So find the values of the trig functions of theta, so some angle, from the information given. So the cotangent of theta is -4/9, and we're told that the cosine of theta is greater than 0. So the cosine of theta is positive. The cosine of theta, remember, is the x value on the unit circle, right? So that might be helpful. So my first step here is I'm going to have a look at this one here. So this means that if I'm on the unit circle here, if the cosine of theta is the x coordinate and it has to be positive, right? And it is, and it does. So the x coordinate is positive on this side, right? The cosine of theta is greater than 0 on that half circle. In fact, I'll highlight it a little bit better. Okay, so that's the realm that we're working in. Another thing that we're going to have to look at is, okay, so we have the cotangent of theta, and if we go over here, right, the cotangent of theta, maybe not this one specifically, go to this one here instead. Copy. Only because I'm told information in terms of cosine of theta, so cosine of theta is greater than 0. So instead of using the opposite over adjacent, that kind of fun stuff, I'm going to look at this one, which has it in terms of the cosine over sine. And that's, I don't know, that's just something that you kind of pick up on really quickly. You can use the other one. So if you wanted to just use these, you can. I just find that it's a little bit more of a leap. So just looking here, because from here, if I know that the cotangent of theta or x, right, remember they're all interchangeable, tx theta, is the cosine of theta over sine theta. So now if I'm told that the cosine of theta is greater than 0, but I have a negative value, right, that tells me something about the sine of theta, right? It has to be negative. That's the only way I can get a negative out of this thing. So I have, I'll do a little bit more of an explanation, just to kind of bring it home. Since the cotangent of theta is the cosine of theta over the sine of theta, and the cosine of theta is positive, the sine of theta must be negative. Oops. Right? that tells me which quadrant I have to be in, right? So here cosine of theta is positive, is on this side, right? My x values have to all be positive. And so up here in the first quadrant, both my sine and my cosine are positive. And then versus down here in the fourth quadrant, my sine is negative, but my cosine is positive. So therefore, we are in the fourth quadrant. Okay. So these are all just things that we're learning about this thing. And it's going to help out for figuring out what this thing looks like. So what I'm going to do is we're no longer on the unit circle, but I can still set up a triangle. Okay, so I can set it up in these axes. In fact, focusing on the fourth quadrant here. Okay. So what I'm going to have is I'm going to have some angle theta here, and then I'm going to bring this up. Okay, so now I've made a triangle. So this is what I was talking about earlier, where before we weren't told anything else about this, you know, what quadrant we're in, or if cosine is positive or negative or whatever. But now that we know that the cosine has to be positive and that the cotangent is negative, now we have to draw our triangle properly in the grid, right? So in the XY plane. So what we know is that the cotangent of theta is -4/9. Okay, so what I know here, and now I'm going to go over, so the cotangent of theta is the adjacent over the opposite. Okay, so the cotangent of theta is the adjacent over the opposite. Okay, which we were also told is -4/9. The adjacent here, that's not the one that's negative, right? Because it's the positive x-axis, so it has to be a value of 4. Okay. But we are going down 9, right? So that's where this -9 is going to come from. And we're going to keep that -9 on there. We're going to say -9 right there. I can still use 4 and -9, right? I can use the Pythagorean theorem to figure out what this value is, right? And so we have 4 squared plus -9 squared is c squared. C is always, and I'll draw that here, c is always the length of the hypotenuse, right? And so I have 4 squared plus, and I can drop the negative. Any negative squared is just the same as the positive squared. So I get 97 is c squared. So then c must be the root of 97, which actually doesn't become anything nice. That's okay. We just leave it as the root of 97. So now I'm going to rewrite this as c, which is the root of 97. Okay. So now let's go back. So I want to find the sine of theta, the cosine of theta, the tan of theta, the cosecant of theta, and the secant of theta. So now that I have my triangle, I'm going to copy these because I'm going to use them to fill in the rest of these. All right. So the sine of theta is the opposite over the hypotenuse. The opposite is -9 over root 97. So you can see how so a ton of work happened. And I mean, I kind of walked you through how to figure out that it was in the fourth quadrant. If you just kind of looked at it and said, oh yeah, well, I have to be in the fourth quadrant because it's negative, that's fine too, right? But you do have to establish this units, or sorry, this triangle so that you can use them. But then once you have all these three sides, then you can just go ahead and plug them in, right? So a lot of those marks are for the work that you do in advance, and then finding all these angles or all these trig functions is not that much work. So the cosine of theta is the adjacent over the hypotenuse. The adjacent is 4 over the hypotenuse, which is the root of 97. C is the tangent of theta, which is the opposite over adjacent. The opposite is -9 over the adjacent, which is 4. Is there another question like this? I feel like I put one on the trig assignment that I posted, because I picked questions that were basically exactly like the ones I want you to do on the final exam. So have a look there. Otherwise, I can I'll hunt some more down, some more trig problems. See if I can. Awesome. So from here, right, we need the cosecant and secant of theta. So let's just finish it off here. The cosecant of theta is the hypotenuse over the opposite, which is root 97 over -9. That negative can float up front, doesn't matter. And then E was the secant of theta, which is the hypotenuse over the adjacent root 97 over 4. In fact, Kayla, I'll make a note here that I should hunt some more down. See what I can do. Let's see here. Okay. So that's it for that question. I know I'm kind of tricky. And that was 19. Okay. I'll go grab 20. All right, so this, whenever you have to write one trig function in terms of another trig function, you're gonna have to use those fundamental identities. So again, really useful handout is this trig formula sheet, and we have not done the laws of sines and cosines, so you can ignore that. But these fundamental identities will save your bacon, especially when you have to rewrite one trig function in terms of another. Okay, so we want to rewrite cosecant in terms of only cotangent. So, and we did one that was quite a bit harder in class. So, but I think we only did one. So that's why this one's actually meant to be an easy one, but because we haven't done a lot, it's not that easy. All right, so what you're gonna do is you're gonna look at the fundamental identities and try to find an identity with only cosecant and cotangent. so that you can morph it so that you have cosecant equals and then something to do with cotangent. Often it'll involve multiple steps, but the ones I've chosen only require kind of 1.5 steps. So if I'm kind of scanning the fundamental identities, I see cosecant and I see cotangent. Okay, so here I've got cosecant in terms of sine x. So if that was the question, right, write cosecant in terms of sine of theta, right? Then 1 over sine of theta, you'd be done, right? Okay, so not quite. Kind of scanning the page, I don't see any cosecants, no cosecants until this one here. So 1 plus the cotangent squared of theta, so x is theta, or if you want to use x, that's fine. It just gets a little confusing because we've got thetas here. Keep you on your toes. But just x is theta, theta is x. Okay? So cotangent squared of theta is the cosecant squared of theta. So here, this is the one that I'm going to use. So 1 plus the cotangent squared of theta is the cosecant squared of theta. Now, one thing that we need to remember for trig identities is, and for trig functions, if they're squared, this is the same as cotangent theta times cotangent theta. So this square behaves the exact same way that you want it to. So there's no worries there. You can take the square root of the cotangent squared theta and it'll give you the cotangent of theta, right? So this is behaving the way you want it to. So that's nice. So I want to rewrite cosecant theta, so not cosecant squared, but cosecant theta in terms of just cotangent. Okay. So what I need to do is, well, first things first, I'm going to just revolving door this, right? The equal sign, I can shift things around so that it's nicer to look at, only because I want the cosecant squared theta on the left-hand side. So nothing's really happening besides rewriting here. Okay. Awesome. 21, 22. So we've got 6, 21, 22. You got it. You got it. So now I'm going to take the square root of both sides. So if I take the square root of the cosecant squared of theta is the square root. Now remember, whenever I take the square root, I end up with the positive and the negative square root. And that's where this quadrant 4 comes in to decide, is it going to be positive or is it going to be negative? So the plus minus the square root of 1 plus the cotangent squared of theta. Okay. So this becomes the cosecant of theta is the plus minus of the root of 1 plus the cotangent squared of theta. Okay. So here, right, deciding between the positive and the negative, in quadrant 4, okay, so I'm going to make a note. In quadrant 4, cosecant is negative, right? So the cosecant is the 1 over the sine, or if you prefer to go back to these little guys, right? The cosecant is the hypotenuse over the opposite. Not super helpful in this case, right? I would probably prefer to look at this one here, remembering that the sine x is the y value, right? So in quadrant 4, the cosecant theta is 1 over sine theta, okay? Which means that in the 4th quadrant, if I'm mapping this out here, right? So here's quadrant 1, 2, 3, 4. in this quadrant, my x is positive, so my cosine is positive, and my sine is negative, right? My y is negative. Sine theta is less than 0. So in quadrant 4, 1 over sine theta is 1 over a negative number. Is negative since sine theta is less than 0. So therefore, the cosecant of theta is the negative root of 1 plus the cotangent squared theta. I'm going to leave it as cotangent squared, even though, I mean, you might be tempted to just write it in cotangent, but that's just cotangent times cotangent. It doesn't really do anything. So what we mean here in terms of this function is that that's the only other trig function that's showing up here. Okay. So when you have to rewrite it, usually you grab one of these, and it's usually from these 3 identities. Okay. And then you have to figure out if it's positive or negative, typically, right? Because you'll see all of these have squares in them. So then you'd have to take the square root, and that's where the positive or negative comes in. But that's why I tell you which quadrant you're in. Okay. So we're going to go to 6, then 21 and 22, or maybe, no, I said, let's do 6 first, jumping around. That's how the test is going to go. So oh yeah, everyone's favorite question here. So we did one of these on your test 2. I think it was test 2. Yeah, there's no way we had it on test 1. So for these ones, right, you're just going to follow a set of procedures. So the first thing is you're going to factor the numerator and the denominator. Usually, so I'm going to pick quadratics. So with quadratics, I use the quadratic formula to factor this thing. And same thing with the denominator. And then we're going to go through each of these steps and see what happens. So we first factor r of x. So r of x is 5x squared minus 20x plus 21 over x squared minus 4x plus 4. Okay. So let's see here, right? Using the quadratic formula here, I'm going to try to factor this thing. It's actually not going to work. I tried it earlier, right? So, and that's okay. That's part of why I picked this one, because we hadn't really seen anything like it. So I just wanted to show you that it's possible. So to factor, apply the quadratic formula. So x is, sorry, the negative b plus minus the square root of, I don't know why I can't do it, b squared minus 4ac over 2a. Okay. Where a is the coefficient on x squared, b is the coefficient on x, and c is the constant. So we get x is negative 20 plus minus the square root of negative 20 squared minus 4 times a, which is 5, times c, which is 21, divided by 2 times 5. Okay, so x then becomes 20 plus minus the square root of, and if you do 20 squared is 400 minus, and then 4 times 5 times 21 is 420. That is bad news bears, isn't it? Right. It's okay, it can happen, and that's why I put it on here. So x is 20 plus minus the square root of negative 20. So because we're not dealing with complex numbers, it doesn't exist. We can't take the square root of a negative, right? We can't take the square root of a negative. So x, or rather 5x squared minus 20x plus 21 has no roots, right? So we can't use those to factor, right? So we don't have to factor it, that's okay. Okay. So the X-Intercepts, right? Oh, and I guess I should factor this little guy. Has to add to, so this one's more reasonable, it has to add to -4 and multiply to +4. That seems like x minus 2 times x minus 2 to me, right? And I'm just going to check x squared minus 2x plus 4. Yeah. So therefore r of x we can rewrite, and so I don't need to factor this thing because I already found that there are no roots, so that's okay. So 5x squared minus 20x plus 21 over x minus 2 times x minus 2, or if you prefer x minus 2 squared, that's fine. Okay, so that's step 1, right? Factoring, and we only factor to make our lives easier later on, right? So part A, the X-intercepts, let's just remind ourselves what the X-intercepts are. The X-intercept is where the y is equal to 0. Now, this thing is only equal to 0 when the numerator is 0, but we just established that it doesn't have any roots, so there is no point where it equals 0. So this is where y equals 0, but since the numerator does not have any roots, we say the X-intercepts do not exist. Which can definitely happen, right? If we're thinking about some sort of parabola, right, and the parabola looks like this, well, if it's just going up and up and up, and if it's facing up and the vertex is maybe here, right? Now I've simplified this thing to be a parabola, but just imagine this, right? That can happen, right? It'll never cross the x-axis down here, so that's fine. That's what we're saying is going on. Doesn't exist. Okay, so that's what D and E means. Part B, so that's all we're doing for A. Find the x-intercepts. You would find them by factoring and figuring out where this thing equals 0, where the numerator equals 0. We found that there is no such place, so the x-intercepts don't exist. Find the y-intercept. The y-intercept is where x is equal to 0. So now I'm just gonna, because we weren't able to factor this easily, I'm just gonna plug in x equals 0 in the original, or even in this kind of revised function, it doesn't matter. So B, the y-intercepts is where x is equal to 0. So r of 0 is 5 times 0 squared minus 20 times 0 plus 21 divided by 0 minus 2 times 0 minus 2. Oh. 5 times 0 minus 20 times 0 is 0. So 21 divided by negative 2 times negative 2 is 4. And I'll try it, but I don't think it simplifies to anything. It doesn't. So I'll just leave it as 21 over 4. Right? You're going to try to leave your answers in exact form unless I tell you to round. Right? So you're just going to leave it as 21 over 4. Find the vertical asymptotes, potentially more than one. Use a sign chart to determine the function behavior around those asymptotes. Okay, so remember the vertical asymptotes are where the numerator is 0, right? We can't divide by 0, so that's where we get these asymptotes from. And then we use the sign chart to figure out what's going on with this thing. So the vertical asymptotes are where the denominator equals 0. So we have r of x is, what was it, 5x squared minus 20x plus 21 divided by x minus 2 times x minus 2. But could we have multiple y, or no. We're just going to have one y-intercept. Yeah, good. And I feel like I'm pleased that you caught yourself, right? Because even I had to think about it. Okay, so y-intercept, no, because then we'd have multiple outputs for one input. So it's not a function. So good call. Exactly. Yeah, I caught myself thinking, no, we only have one y-intercept, but not thinking why. Why is that? That's why. It has to be a function. All right. Cool. So this is where the denominator equals 0. So x minus 2, regardless of which one, you can write it as x minus 2 squared. I just like to see them side by side. So x minus 2 times x minus 2. X equals 2 is going to give me 0 in the denominator for both of these, right? And so here, x equals 2 is a vertical asymptote. Okay. Now, for the behavior, it's a lot easier to figure out if we're going to positive infinity or negative infinity if we've factored the top, but we don't have to, right? So what I'm going to do is I'm going to set up a kind of a table here. So I've got my number line. There's only one vertical asymptote, right? So I only need to plot this one point at 2. Okay. And around this point, right, I just need to figure out at this vertical, so I've got this vertical asymptote here, so it's either going up towards infinity or it's coming and approaching and it's rapidly going towards negative infinity. So those are my two options, and I just need to figure out how it behaves on either side of 2, right? So here on this side, we've got x is going to 2 from the left, right? We use that. X is going to 2 from the left with that negative up top, right? So if I'm coming towards 2 from the left, maybe something like 1.9, right? And then if I'm coming from approaching 2 from the right, then maybe I'll use something like 2.1 to kind of gauge if it's going in the positive or negative direction, right? So on this side, I have x going to 2 from the right. Okay. So I'm just going to use test values here. Let's use 1.9, and maybe on this side, I'll use 2.1. So I want to be close enough to 2 that I can kind of convince myself that no weird changes are going to happen, right? And then we're going to find that it goes up and up on both sides. But what I'm going to do, instead of using that sign chart that we used in class, because I don't have it factored, and I just want to show you that you don't necessarily need to have it factored. So what I'm going to do is I'm just going to plug in x equals 1.9. If I get a positive value, it's going up towards positive infinity. If I get a negative value, it'd be going down to negative infinity. So now r of x is 5x squared minus 20x. I'm just going to write it down here. Plus 21 over x minus 2 squared, just to save a little bit of math. I'm just going to divvy up the page here so I can kind of keep those two separate. So I'm going to do 5 times, and then I'll highlight 1.9 squared minus 20 times 1.9 plus 21. (1.9 minus 2 squared). So 1.9 squared times 5 minus 20 times 1.9. Make sure you do the 20 and 1.9, multiply those first and then subtract them. Plus 21. And then divide it by 1 bracket 1.9 minus 2 squared. I get 105. Okay, so because it's positive, I am going to say that this thing is going up towards positive infinity. Okay. If it had been negative, it would be going down towards negative infinity. So now I'm going to do the same thing on the approaching 2 from the right, using a value to the right of 2, so 2.1, for example. But doing the exact same thing. So r of x is 5 times 2.1 squared minus 20 times 2.1 plus 21 over 2.1 minus 2 squared. And maybe I should highlight these test values. Depending on how close to 2 you want to go, right? We don't need to make our lives that difficult. But if we let it be exactly 2, it's not going to work, right? Because 2 minus 2 is 0, so then you're dividing by 0, which we can't do. So that's the pickle. All right, 2.1 squared times 5 minus bracket 20 times 2.1 plus 21 divided by bracket 2.1 minus 2 end bracket squared end bracket positive 105 again. It's no fluke, right? They're all squared. Yeah. So it's positive, and so what that tells me here is that it's going to be going like that. Which makes sense, right? If it's kind of approaching the same point like this, then, and we moved an equal distance around 2, then, yeah. So don't be too thrown off by getting the same number. Kind of checks out. All right, so now we've decided at this vertical asymptote, right, we're going to go up to positive infinity as we approach 2 from both sides. Okay, so we're getting an idea of what this thing looks like. What was the next thing we had to do? Man, this is a big question, right? Find the horizontal asymptote. The horizontal asymptote, right? Remember, it depends on the degrees of the numerator and the denominator. If the degrees are the same, which they are in this case, then we take the coefficient of the first one over the coefficient of the denominator, or the coefficient of the numerator over the coefficient of the denominator. I can't remember exactly where that was. Well, it was section 3.6. Oh, that's the problem. I had to restore my iPad, so I lost all my notes. So I can't even go there. Okay, that's okay. Oh, that's a trig formula sheet. Maybe I'll go to that other formula sheet that I posted just to see if it has anything about the asymptotes. Oh, here's the Pythagorean theorem. That's nice. Nothing about asymptotes. So you'll need to jot that one down for sure, because I'll get you to do something very similar. Yeah, that'd be great. If you have it handy, only because I don't. Oh, maybe I do actually. Hang on. 3 point. Did they come over? No, of course not. If you're okay to take my word for it, I'm ready to just jot it down. So D, the horizontal asymptotes, oh, I know, I'm on Moodle. Here we go. Let's see here. That would have been rational and polynomial functions part 2. Slowly but surely get there. 3.2, 3.3, 3.6. Just to have them, let's bring them in. So here, so if we have some sort of rational function like this, then if n is less than m, so n being the degree of the numerator and m being the degree of the denominator, then we have a horizontal asymptote at y equals 0. If n equals m, which is the case that we have, then we have a horizontal asymptote at y equals an over bm. So that's the coefficient of the numerator over the coefficient of the denominator. And then if n is greater than m, then there's no horizontal asymptote. I think. And maybe I'll make a note here, 3.6 notes, right? All of these are in the 3.6 notes. All right, so since the degree of the numerator equals the degree of the denominator, we have a horizontal asymptote at y equals, and where is it? Let's go to the original because it's easier to look at. 5 over 1, so just 5. Good. Okay. That's D. E. Okay, so now we're going to pick the right graph. So again, I just want you to pick the right one and just indicate which one it is using, and I put letters on it this time, make it a little bit more helpful. So we have to collate all the information that we've put together so far, right? And so we know that we have a, well, let's start with a horizontal asymptote at y equals 5. So here we have a horizontal asymptote at -5, -5, right? Right, so both of these two are out. Okay. These both have horizontal asymptotes at positive y equals 5, so that's good. So now I know, okay, I know my behavior around the vertical asymptote is both going up to positive infinity, so that would have eliminated these two as well. Now, the only thing that's different about these two is that for C, the vertical asymptote is at x equals 2 versus the vertical asymptote at x equals -2. So because we were at x equals +2, right, this is the one that we want. So this one, vertical asymptote at x equals -2, and that's wrong. So then we have C. But wait, there's more. Domain and range, but we're just going to use so I just want you to use the graph to figure out the domain and range. In interval notation, the domain is all the possible x values. So we know, okay, and one thing that I will say is if you happen to pick the wrong graph, then that's okay, as long as you do the domain and range according to the graph that you picked. It takes me way longer to mark that way, but I just think it's fair, right? How are you supposed to know that you picked the wrong graph? So anyways, so I will follow through, and that goes for any of these questions, right? If you follow through kind of sort of logically, depending on how big of a mistake you made in the beginning, right? If you follow through and you use things properly, then I'm happy, right? And I can follow and I can give you as many marks as possible. But depending on the initial error. So here, right, even if you picked D, and you told me that the domain was from -infinity to -2, and then picking up again at -2 to +infinity, I'd be okay with that because that's the graph you chose, right? So in this case, we're going from -infinity to +2, right? We're doing the proper one. So we have this little gap at +2, so that's why we have to have a round bracket, right? And then we have a union, right? Picking, that's how we connect these intervals. So, but then picking right back up at 2, right? Very close to x equals 2, and then going to +infinity. So again, we need to have round brackets here at these asymptotes because we can't get to those values up to +infinity. No? Same thing for G, but the range, so the range is the Y values. So again, here, the Y values look like they're going from +infinity, sorry, I don't know why I said it from +infinity, from 5, but not including 5, right? So we have a horizontal asymptote at 5, so we can't quite get to 5, but we're going from 5 up to +infinity. So from 5 to infinity. Okay. And I think that was it for, which question is this? Wow. 6. All right, just going through the list here. Next on the docket, 21 and 22. Unless we have questions about this one. So this one's long, right? But as long as you kind of follow, and the steps, in case you don't like how I've listed, you know, A, B, C, the steps that we're following here are right here. So you have to factor the numerator and the denominator, and then here it just goes through and it tells you what the X-intercept is and what the Y-intercept is, and then how you find the asymptotes, and then I'm not getting you to sketch a graph, there's no point. I hate sketching, so I'm not going to make you do more than you have to. Okay, 21, and then followed by, wait, oops, 22. All right, use the inverse function property to determine whether f and g are inverses of each other. Now it helps to remember what the inverse function property is, so let's outline that first. Right, the inverse function property says that f and g are inverses of each other if f of g of x is equal to x, and so it has to be true for both of these, and g of f of x is equal to x. This is a function composition, right? So if you prefer, then you could write f composed with g of x, right? But I think a lot of people don't love the composition, right? But when we write f of g of x, it's a little bit easier to read, but I'll just put it on here just to be proper. So g composed with f of x, which is g of f of x. So what we need to do here is we need to show that f of g of x is equal to x, right? So things are going to cancel out and we're just going to be left with x. And then same thing, g of f of x, everything cancels out and we're just left with x. Okay. Usually I like to do these side by side, mostly because it saves space, but also so that you can kind of see similarities. So what I'm going to do is I'm going to start up here and I'm going to say f of g of x is equal to, and maybe I should scoot this over to the far left. So f of g of x is, g of x plus 9 over g of x minus 9, right? Wherever I see an x, I'm going to put in g of x. And so g of x plus 9 over g of x minus 9, where g of x is this 9x plus 9 over x minus 1. So now I'm going to write 9x plus 9 over x minus 1 wherever I see a g of x. Gets a little bit nasty, but things will cancel if they're inverses of each other. I'm not going to get you to do all this work for no reward. Although, if you did land on something that doesn't cancel to x, and you told me that they're not inverses of each other, that's proper, right? So just keep that in mind. You always just want to do what's proper. Got another request? 13a and 14a. Got it. Plus 9 over 9x plus 9 over x minus 1 minus 9. And you know what? I'm going to throw some big brackets around this g of x just so I can see where I put things. Now, what we need to remember, right, is I have a fraction here. So just talking about the numerator, if I have a fraction plus a number, I have to convert that into a fraction with a common denominator, right? So what I'm going to do is I'm going to multiply this side by x minus 1 and then have it over that common denominator of x minus 1. So this becomes 9x plus 9 over x minus 1 plus 9, and then I'll show it here in a different color, times x minus 1 over x minus 1. Divided by, and then same thing here, 9x plus 9 over x minus 1 minus 9, and then I'll show again the same thing, times x minus 1 over x minus 1. Right, multiplying by 1 doesn't change anything. Okay. Now I've got this common denominator, so I can smush this together, right? And I can also expand this 9 inside, so I get 9x minus 9. So a lot's going to happen here. I am kind of moving a little bit quicker. So if there's something that doesn't make sense, gotta stop me. Okay, so I put the numerator over a common denominator, and then I'm going to do the same thing with the denominator, but here I've got a negative 9 coming in, so I need to do negative 9x plus 9. So I get 9x plus 9 minus 9x plus 9 over x minus 1. And I'm going to put this x minus 1 in brackets. Okay, so what I'm going to do is I'm going to cancel as much as I can, right? 9 minus 9 goes away, and 9x minus 9x, that's going to go away. And then I'm going to be left with a simpler fraction over a fraction, which I need to flip and multiply. I know you guys love fractions. Okay, so 9 minus 9 goes away. 9x minus 9x goes away. Okay, so now I can rewrite this as 18x over x minus 1 divided by 18 divided by x minus 1. Fraction over a fraction. I can flip the denominator and multiply. So I get 18x over x minus 1 times x minus 1 over 18. So this is why I put the x minus 1 in brackets, just to indicate or to kind of remind myself that they're one thing. Because now I can cancel these, whee, as well as the 18 over 18. And I'm just left with x. But wait, there's more, right? Now I have to do the same thing, but on the other side, right? But that's a good step in the right direction. So here, now I'm hopeful that the other one is gonna work out to be x as well. So if it doesn't, I probably did something wrong, right? But we have to check both sides. So what I'm gonna do is I'm just gonna kind of break up my page a little bit here. Whee. And do g of f of x on this side. So g of f of x is now in g, wherever I see an x, I'm going to put f of x. It's going to look very similar to what we just did, right? So it's just an exercise in fractions. 9 times f of x plus 9 over f of x minus 1, which is 9 times, and then f of x is x plus 9 over x minus 9. Plus 9 over f of x, which is x plus 9 over x minus 9 minus 1. Same deal. I need to have a common denominator, so I'm going to multiply 9 by x minus 9 over x minus 9, and same thing with the minus 1 by x minus 9 over x minus 9. So I get, I'm going to keep this 9 outside, x plus 9 over x minus 9, oops, plus 9 times x minus 9 over x minus 9 over x plus 9 over x minus 9 minus 1 times, and then just forcing that common denominator of x minus 9. So now, in the same sweep, I'm going to bring this 9 inside. So I get 9x plus 81, right? 9 times 9. Yep. And then same thing, bring this 9 inside here. So I get 9x plus 81 plus 9x minus 81 over x minus 9 divided by x plus 9 minus x plus 9 over x minus 9. Again, things are going to start to cancel out. Notice that they have very similar behaviors, right, at each step. So, right, if you do a lot of these, then you'll be really good. 81 minus 81 cancels out. And then I have x minus x, fine. So now I have 9x plus 9x puts me at 18x over x minus 9 divided by 18 over x minus 9. Fraction over fraction again. Now I can flip and multiply. And in fact, I'm going to emphasize that x minus 9 is one thing because I want to cancel it later, right? So I don't want to get thrown off here. So I get 18x over x minus 9, oops, times x minus 9 over 18. X minus 9 cancels with x minus 9, and 18 cancels with 18. So I'm left with x. All right. So now don't forget your conclusion. You did all that work. You have to tell me why did you do it? Show me what it means. So since f of g of x is equal to x, which is equal to g of f of x, right, or some form of that, right, we can conclude that f and g are inverses of each other. F of x and g of x are inverses of each other. A lot of work, right? But just kind of keep your cool and remember you need to have a common denominator and keeping those negatives and things will cancel out. So I think that was 21, oh, and then 22, and then we'll do 13a and 14a. So we have to find the inverse of this thing. There are a couple of different ways that you can do it. I always follow the same way, but if you're, kind of going online and watching Khan Academy, I'm not sure how Sal does it. It's pretty common to do it the way I do it, but sometimes you'll solve for x and then switch your x's and y's. But anyways, here are the steps that I follow. So to find the inverse, step 1 is write y equals f of x. So what that means in our case is that y equals x minus 5 over x plus 5. Step 2, swap x's and y's. So then I have x is y minus 5 over y plus 5. And so just wherever you see an x, make it a y, and wherever you see a y, make it an x. Step 3, solve for y. Solve for y. This is now f inverse of x. Okay, so that new y that you've solved for is the inverse. So I start here, right? So I'm just going to rewrite this on the next page because I'm dealing with the page break here. So I've got x is y minus 5 over y plus 5. And I'm slowly going to migrate things over so that I can start to collect like terms, especially the y's, so I can solve for y. So I get x times y plus 5 is y minus 5. Okay. So now I have a y here and a y here. I'm going to expand this out to try to get at that y. So now I have xy plus 5x is y minus 5. Now in kind of a fast move here, I'm going to move the y over to the left-hand side and the 5x to the right-hand side. So I get xy minus y is negative 5 minus 5x. Okay. Now I can factor out this y, right? And that's how I'm going to be able to solve for y. So I get y times x minus 1 is, and if you want to, you can pull out a common negative 5 here. I don't really see the point, so I'm just going to leave it. Don't mind if you do too. Negative 5 minus 5x. So then y, if I'm solving for y, I have to divide both sides by x minus 1. So I get negative 5 minus 5x over x minus 1. And so this is my inverse function. Therefore, f inverse of x is -5 minus 5x over x minus 1. And I'll just do x minus 1. Don't need those brackets. Okay. Got 13a and 14a on the docket. Keep an eye out for questions, but I'm just going to keep going. Hopefully that helped, Nick. A little bit. At least now it's on paper. I'll post these notes after, so cool. And it's been a while since we did inverses and all that stuff, so it's good refresher. 13a and then 14a. Here we go. Find the exact value of each expression if it is defined, and then I don't want you to use your calculator, which is sneaky, right? And it's using the inverse of these functions. So one thing that we need to remember is that sine inverse of 1 is the same thing as saying, well, this is equal to some angle theta, right? This is actually the exact same thing that we did earlier, where we had a function wrapped around on the outside, making it a kind of a next level type of problem. So here, what I'm going to do is I'm just going to shift. So I add this theta here because that's true. I can shift this sign over, and then it's just telling me that sine of theta is 1. So now I can have 1 is the sine of theta, right? Just kind of shifting that inverse sign over. If you think about our kind of unit circle here, sine theta is the y value, right? So where y is 1, that only happens here, right? This is at 0, 1. So sine theta equals 1. That's the only place that this can happen. Another thing we need to remember is that cosine, so the inverse cosine goes from 0 to pi, right? So it's this upper half moon. Sine and tan, so the inverses of sine and tangent are on the right-hand side of the circle, right? So if you have a choice between two angles, one over here in the first quadrant and one over here in the second quadrant, for example, then you have to choose the one in the first quadrant, just because of how we've restricted sine to get the inverse sine. So here, right, if sine theta is equal to 1, well, the angle or the point here, right, that makes that happen is pi over 2. So here, so theta is pi over 2. I know you didn't ask for B, but how about we do B? And then you can think about why C is undefined. Remembering that you're on the unit circle. Okay. So for B, same idea, right? You've got the sine inverse of root 3 over 2. Okay. First thing I'm going to do is I'm just going to shift that, because I don't like looking at sine inverse, right? But I don't mind, well, I can't speak for everyone, right? But I don't mind so much looking at the sine of theta equals √3/2. So here, what I have is I have √3/2 is the sine of theta. I'm just kind of shifting things over. What does that tell me? It tells me that the y value on the unit circle has to be √3/2. Okay, so, and remember on that trig formula sheet, we've got this fancy pantsy unit circle. I'm going to make it a little bit smaller so I can have it on the same page, right? But now I'm looking for y values that are √3/2, positive √3/2. Okay. So, okay, y values that are positive √3/2, that one, and this one, right? The rest, right, sine has to be positive, and so that's only positive in the first and second quadrants because it's the y value. Right here, they're going to be negative. Here I'm at negative √3/2, negative √3/2, right? And so I have two choices. So what we said was, well, sine inverse, the inverse sign is only defined on this half, this right half. So in quadrant 1 and quadrant 4. Okay. So since sine inverse of theta, or sorry, sine inverse is only defined in Q1 and Q4. Oh, I tried to keep it on the same page, but fresh page. And Q4, now I didn't need to write it so small and weird. We know that theta must be pi/3. And I'll say, and can't be theta equals 2 pi/3, even though that's an option, right? Here we see that it's an option, but we need to kind of put the brakes on and say, well, actually, the sine inverse can only be in the first and the fourth quadrant. So this one's out. Right? Sine inverse of 5, let's think about it. Well, I'm restricted to the y values here on this, this half moon, right, or this half circle. So my largest possible sine theta value is 1, and my smallest possible sine theta value is -1. And so sine inverse of 5 is undefined, right? Because I'm restricted to sine inverse is only between -1 and 1. Or can only take values between -1 and 1. Okay. I'll leave that one for you to articulate. Okay. Let's do 14a and potentially a couple more if we see fit. So find the exact value of the trig function at the given real number. Okay. So here, what I want you to do is, we've got these weird trig functions, right? So, but we've got these familiar angles, right? 7 pi/6, -7 pi/6, -11 pi/6. Negative, remember, just means that you're moving in the clockwise direction. So first off, I'm going to grab this unit circle here and hopefully be able to erase these. Awesome. Okay. So 7 pi/6, I've got 7 pi/6 here, right? So I know that the cosine of 7 pi over 6 is negative root 3 over 2, and the sine of 7 pi over 6 is negative 1/2. Right, so I can use those to find the cosecant. Let's talk about these negative values, right? So here, 7 pi over 6, I went a half circle and then pi over 6. So now in the negative direction, I'm going to do the same thing. I'm going to go a full half circle, and then pi over 6 puts me at 5 pi over 6. So negative 7 pi over 6 is actually coterminal with 5 pi over 6. Thinking about a negative 11 pi over 6, you do the same thing, right? 11 pi over 6, that's so close. That's just pi over 6 away from a full rotation, right? So here you're going to go to this pi over 6 here. Right. All right, so I'll make a note here that this is coterminal with 5 pi over 6. And this one here, negative 11 pi over 6, is coterminal with pi over 6, right? That's just so that we can skip to just solving the problem, right? But that's part of solving it when you're doing it. But just so we have those laid out. So really make sure that you have some version of this unit circle handy, right? Because you're going to refer to it. Okay. The other thing you're going to want is these guys here, these fundamental identities. Cosecant, secant, cotangent. So I'm going to grab these as well. Okay, so the cosecant of 7 pi over 6, I can rewrite, so part A, the cosecant of 7 pi over 6, I can rewrite as 1 over the sine of 7 pi over 6. 1 over the sine of 7 pi over 6. From this nifty unit circle, 7 pi over 6 has a y value of negative 1/2. So I can replace sine 7 pi over 6 with negative 1 over 2. And so I get, this is the same as 1 over negative 1 over 2. This is essentially a fraction over a fraction, right? 1 is 1 over 1 over 2, but negative, right? So if I flip and multiply this, I get 1 over 1 times negative 2 over 1, putting me at negative 2. Let's do B as well, just, and then you can, I'll leave you to do the cotangent. Okay. The secant of negative 7 pi over 6 is the same as the secant of 5 pi over 6, right? Because we're at the same point on the unit circle. So it doesn't matter how you got there, whether you got there clockwise or counterclockwise. If you end up at the same point, you're at the same point, right? So the secant of negative 7 pi over 6, let's see here. The secant of negative 7 pi over 6 is the same as the, oops, sick. I don't know why I said that. Secant of, what did we say, 5 pi over 6. And from the identities, right? Whoa, what happened? We've got the secant of some angle is the same as 1 over the cosecant of that angle. And so now I'm going to rewrite this as 1 over the cos of 5 pi over 6. But the cosine is the x value at 5 pi over 6. And so the x value at 5 pi over 6 is negative root 3 over 2. Right? So I get is 1 over the negative root 3 over 2. If I flip and multiply this thing, right, and I'm going to keep it on one page, so I get weird. This, right, if I flip and multiply 1 over 1 times 2 over root 3, and then it's negative, so I get negative 2 over root 3. Hopefully that's what it's supposed to be, but who knows. Let's see here. I did some of these. Good. It is. And maybe, just maybe, just so it's on the same page, negative 2 over root 3 properly. All right. And then C should be okay. Any other questions?
Are you able to just like explain the unit circle? Like you kept saying like quadrant 1 was like sine inverse. So like, just so I can like label it again.
Okay, so what I'm gonna do, I'm just gonna grab this one. Is this because that's the one that you want, right?
Yeah.
You got it. I'll just go through all the components that we kind of need. All right. So first things first, this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. Okay. This y value, and I'm just going to do it in general terms here. So if you have x, y, that's the same as the cosecant of theta, comma, sine theta. So whatever the x value is, that's the cosine, and these are your angles. So that's the next thing that I'll put on here. So here we've moved theta equals pi over 6. And then pi over 4. So we've got these kind of classic cutoff points of pi over 6, pi over 4, pi over 3, and then pi over 2. So we move in multiples of those. And for the majority of any type of trig problem, those are the only multiples that you'll need, right? So makes it nice, right? So you'll have some multiple of pi over 6, right? So here you move pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6 is pi, right? And then you have another full half circle, right? For a total distance of 2 pi. Because the cosine is the x value, right? Cosine is going to be positive in this quadrant 1 and quadrant 4. And cosine is going to be negative in quadrant 2 and quadrant 3, right? Because now you're on the negative x-axis. Because this point here is at 0, 0. And because you have a radius of 1, that's why you're going from 1, 0 to 0, 1 to negative 1, 0 to 0, negative 1, and then back to 1, 0. Right? And so you're at the origin, and then you're just kind of tracing all the way around the unit circle. So this distance here is always going to be 1. What else can we say about this thing? Oh yeah, and then our y values are positive in quadrant 1 and quadrant 2. So sine is positive in quadrant 1 and quadrant 2, and sine is negative in quadrant 3 and quadrant 4. And then you add another layer when you talk about things like the tangent of some angle, which is the sine over the cosine, right? So if sine is negative, right? For example, if you're in quadrant 3, you've got a negative over a negative for your tangent, so your tangent would actually be positive. Versus here, you've got a negative over a positive, so then in quadrant 4, your tangent would be negative. Right? So it just depends on the sign of, but you can boil it all down to the cosine and the sine. So that sort of. Awesome. Any other questions? Okay. Sounds good, Raphael. Oh, sorry, Nara. No problem. Oh, Nick's asking if we can do 8. You got it. Oh, some logs here. Hi, Nara. All right. So we're going to have to solve this thing for x, but that means we also have to use I'll go double time. No, that's fine. So we have to make sure that we're working in the same base, right, before we try to combine things. But then if we're working in the same base and we're adding, we actually just end up multiplying inside. And those are just the log laws that we know and love. So we have the log of base 14 of x minus 3, just writing out the question, plus the log base 14 of x plus 2 is equal to 1. From the log laws, I know I can combine these as one log, so log base 14 of x minus 3 times x plus 2 is equal to 1. What I'm going to do is I'm going to expand this out to get a quadratic. And then, because I'm working in log base 14, I'm going to take 14 to the power of this whole thing, which also means I have to take 14 to the power of 1. And that's going to get rid of this log, and that's how I'm going to shake out the x. So I'll keep it outside for now while I expand. So times x squared plus 2x minus 3x minus 6 is 1. So I have the log base 14 of x squared minus x minus 6 is 1. Raising both sides up to 14. I never know how to say it properly. And you know what? To keep it all on one page, I'm gonna just smush it a bit here. Smush. 14 to the log 14. Right, and I only chose 14 because it's the base. X squared minus x minus 6 is 14 to the power of 1, making sure that you do it on the right-hand side too. That's probably the #1 mistake people make. This essentially cancels, that's why we did it. So now this thing is going to drop down, and so I have x squared minus x minus 6 is 14. If I move that 14 over to the left-hand side, I'm going to have a quadratic, and so I can use the quadratic formula to solve it. X squared minus x minus 20 is 0. And now I can use the quadratic formula to solve. So I have x is negative b plus minus the square root of b squared minus 4ac over 2a. X is negative 1 plus minus the square root of negative 1 squared minus 4 times 1 times negative 20 over 2 times 1, which is 2. And I have 4 times 1 times negative 20. So I have 1 minus negative 80, which is 81. So I have 1 plus minus the root of 81 over 2, which means I have the root of 81, which is 9. So 1 plus minus 9 divided by 2. X is 1 plus 9 over 2, and x is 1 minus 9 over 2. Right? From the quadratic, we get two solutions. 1 plus 9 is 10 over 2, which is 5, and 1 minus 9 is negative 8 over 2, which is negative 4. Whee! So it's got that added element of the quadratic formula. Good.
So quick question on that. I think on the solutions there, it only shows the one answer. Would you only want one answer on the test?
I forgot. I didn't check the domain. Thank you. Thank you. Because I'm working in a log, I can't take the log of 0 or a negative number. So I want to make sure that, okay, 5, if I plug 5 in there, thank you. Rookie mistake I'm making here. 5 minus 3 makes a positive, so that's good. 5 plus 2 is definitely positive, so that's good. So 5 is, so x equals 5 is in the domain. Kind of check mark. Negative 4 probably isn't. Let's see here. Negative 4 minus 3 makes a negative, right? So it's not in the domain. Negative 4 plus 2 is also not in the domain. So we can't have it as a solution for x in these logs. Good. Okay. Go eat. You had a final today. I'm just making you work hard. I'll be around if you have questions tomorrow. Yeah. But at least you had some forced studying tonight, or today, I guess. You're welcome.
Yeah, I'm gonna head out as well. Thank you for the help.
No problem. All right. See you later, guys. I'll stop this recording here.